Essential tremor is the most common neurological movement disorder in the United States. In the most common forms of tremor, any normal movement of the affected limb is accompanied by uncontrolled rhythmic shaking. Deep brain stimulation has been shown to be an effective method for suppressing tremor. However, current systems are constantly on, regardless if the limb is actively tremoring or not. This results in more power being used than needed and potentially additional exposure to unintended side effects. Researchers at the NSF Center for Sensory Motor Neural Engineering are working on one solution to this problem, which is to include additional sensors that will directly sense the tremor. This will allow us to decide when and how to stimulate. By ensuring the implant is stimulating only when needed, the resulting system will draw less power from the implanted battery and also limit any exposure to side effects to times only when the stimulation is necessary. In order to close the loop, we are building several wearable sensor systems to monitor essential tremor in real time while a patient goes about their day. This includes a wirelessly connected inertial sensing watch worn here. The system utilizes a 9-axis IMU that includes an accelerometer, gyroscope, and magnetometer. Displayed on screen is a single axis of accelerometer readings. The neurostimulator we are utilizing is the Medtronic PC+S. The implant uses the Nexus system to allow a computer real-time command and control the device, as well as providing access to sense data from the electrodes. For simplicity, we are displaying the output stimulation waveform on a benchtop oscilloscope. In this example, the stimulation is shown as a high-frequency spike train. Our lab has been utilizing the Medtronic Nexus system to prototype closed-loop systems. In this experiment, a pre-programmed stimulation pattern is triggered when the limb tremors. After the tremor subsides, the stimulation is turned off. Passive or tremor-free movements do not trigger stimulation. Essentially, we are limiting DBS stimulation to be only active during the time it is required. In this next experiment, we demonstrate a system where the stimulation parameters are directly controlled by the magnitude of the sensed tremor. As the tremor severity increases, the stimulation power also increases within bounds set by a clinician. This experiment shows that we are able to implement tremor mitigation strategies that not only control when the stimulation is delivered, but what form the stimulation takes as well. These closed-loop systems are fundamentally more robust against day-to-day variations in the tremor, and will limit the power of stimulation to only the level needed. However, the systems we have demonstrated so far are not mobile enough to travel with a patient. Shown here is an example of a mobile and wearable system. As before, a Warren sensor is wirelessly sensing the tremor state, and the Nexus system is communicating with the neurostimulator. The Nexus system has been modified to replace the wired USB connection with a Bluetooth connection that now runs off of battery. A smartphone is responsible for maintaining the connection between the user's input, the sensors, and the neurostimulator. To demonstrate the functionality of this mobile system, we will again be using the Medtronic PC+S neurostimulator and an oscilloscope to monitor the output. We have already begun app development for these mobile system prototypes. For example, the system is capable of acting as generic remote control for the neurostimulator, allowing a user to adjust their own stimulation level within bounds set by their clinician. Using Bluetooth-enabled wearable sensors, we can also emulate the closed-loop experiments already shown. Once again, the wearable sensor can be used to trigger a pre-programmed stimulation pattern when the patient begins to tremor. We can also demonstrate the proportional control strategy shown previously. Here, the magnitude of the sensed tremor directly maps to the stimulation power. These systems show that the tremor mitigation prototypes we are developing will not be limited to laboratory or clinical settings. Closed-loop neurostimulation systems will need to be mobile enough to travel with patients as they live their lives outside of the hospital, and this work demonstrates an important step in that direction. Thank you for watching.